The ideas expressed in the following presentations are those of the speakers and do not necessarily reflect the views of ACI or its committees. ACI web sessions are recorded at ACI conventions or other concrete industry events and will be made available for viewing free of charge for 1 week. Thereafter, they will be archived on the ACI website or added to ACI's online CEU program, depending on their content. You can earn continuing education credits through ACI's online CEU program. Visit www.concrete.org to register. ACI conventions provide an opportunity for networking and for keeping up to date with the latest in concrete technology and practices.
Next up is Narayanan, Neithalath, if it will come up here.
Thank you. Good afternoon, everybody. I'll be really quick, and the title in the book is slightly different. I saw a lot of kinetics and early age stuff, so I thought I'll focus on the durability stuff just to give you a little bit of a different flavor. So the basic idea is we are trying to look at alkali activation of slag, look at the durability properties, and basically we are looking at, and there's a lot of the sustainability stuff that people have talked all over, so I won't bore you with that again. The idea is, we've talked in the morning, we talked about the activator type and chemistry influencing the process. Typically, sodium and potassium silicates are used. Reaction products is a calcium aluminosilicate gel with a low enough calcium to silica ratio with sodium and potassium incorporated in the system. So that's the basic idea. But what we are trying to look at is how does the microstructure of this material change, long-term microstructure, and how does that in turn affect the chloride transport. So basically we know that chloride transport is influenced by the pore structure, pore solution composition, and the external electrical field, whether you use what kind of accelerated test method for chloride transport. So this presentation looks at two different types of activating alkalis. Typically, sodium silicates or potassium silicate solutions are used because they are better activators. But from a point of view of EC constructability, powders are also better because you can then make a one-component system, just add water kind of systems. So we're looking at blends where you can use powder activator, blend it with the slag, and have one-component system. But how does the microstructure change if you have that kind of an activation? So what we look at are material microstructure, experimental studies using mercury intrusion for asymmetries, and electrical impedance and associated model-based interpretations to show what is actually happening in the microstructure before and during transport. And then gets you a simple method to predict the migration coefficient. And again, this is something that's universal. We have developed for all types of concretes. I'm just showing the case for alkali activated concrete. So two different slag contents, total alkali content of 0.05, we did, or 5%, we did a higher one for powder too. Sodium silicate with a silica modulus of 2, sodium hydroxide can be used to bring it down to 1.5. Sodium silicate liquid has silica modulus of 2, 1.5 and 1. So we did 3 different ones, but these two are the commonly used numbers. So, mechanical properties, if you look at compressive strength, your powder activated mixes will give you only about 30 megapascal. With liquids, you can go to 80 megapascals or even higher depending on the type of slag. But the reason is that, you have with solid activators, reduction in the solution. The compromise you are getting is for a system that you can work very quickly with without the need to store liquid separately somewhere else. Accelerated transport test, we did both rapid chloride permeability test, everybody seems to like it. Non-steady state migration to get the diffusion coefficients, chosen because of course not pure science but popularity too. Some balance. We know that RCPT has deficiencies, but the advantage is that both of them are electrically accelerated. So there are some similarities between those which we will make use of in trying to understand what they do. So here are RCP and steady state migration values. What you see here are the powder activators. See here are the liquid activators. You can certainly see that the powder activators have, remember, they have lower strengths but much lower transport values with respect to RCPT values. When you look at non-steady state migration, not very different between solid and liquid except when your alkalinity is very low. So this itself will tell you straight away that there are microstructural differences between these two activated materials, and also it tells you RCP is not a great way to characterize mixes where you have these kinds of changes. Just to give you a comparison, ordinary Portland cement concrete 56 days is about there, with silica fume, 6% silica fume at 56 days about here. So that's the range that you see for powder activated mixes. With a liquid sodium silicate, you're getting between 20% fly ash, 6% silica fume. So you can really get very comparable values, even better values in terms of chloride transport when you have activated slag. So here are the observations which I just told you about already. The important one is that no significant change when you have powder activation between 28 and 56 days. It doesn't seem to do anything further. Same trend was seen in the compressive strength results also. With a non-steady state migration, again, the results are now much more in line with what you expect. You don't see dramatic drop for one type of concretes, but the reduction with liquid activated or solution activated sodium silicate increases with the silica modulus or silica content more than the reduction RCP values, and we'll talk more about that when we do the microstructure. So all the values are comparable to or lower than the non-steady state migration values of corresponding OPC concretes, which gives you an indication that yeah, you can make them for durability levels comparable to or better than OPC concretes. And remember, the slag content was 300 kilograms per meter cube or 400, but most of them are 300 kilogram per meter cube mixes. So very low values of binder. One thing to note, because we have two different activated parameters. One is the N value, which is the sodium oxide content, and the other is the MS, which is the silica to sodium oxide ratio. So if you basically multiply that, you effectively get the silica content in the activator. So you can nicely trend those non-steady state migration values at 28 and 56 days to the silica content in the activator, irrespective of the sodium oxide content for the range that we have studied. It's an easy way to start looking at what kind of values do you need for a target non-steady state migration value, something to be used as a guide before you start designing your mix. Now, the pore structure is quite interesting. What you see here are all pore structure of powder sodium silicate activated mixes at 28 days. You have about 16 to 17% total pore volume, or 16 to 17% centimeter cube per gram total pore volume for all of these mixes. The pore sizes, though, come down when the alkalinity is higher. So you can, from 0.07 microns, the characteristic pore size comes down to about 0.01 microns. So you can say that reduced chloride permeability and non-steady state migration values can be attributed to pore size reduction. I'll show you some proof of this further down. But if you look at the liquid activated concretes, you can see that the porosities are much lower. We talked about 16%, you're about 12% porosity now, but the pore sizes are much higher. So lower porosity but higher pore sizes here, and these two have implications on how transport happens. So here is some data on looking at conventional concretes and trying to look at what influences transport more. So here is porosity and pore connectivity. So you can have silica fume mixes within the same range of porosity. With silica fume you can have extremely low pore connectivity. Plain and fly ash mixes, the porosity range is quite wide and pore connectivity doesn't drop that much. And all these are data from electrical impedance measurements that we've done over time. And again, you can see that pore connectivity with equivalent pore sizes, you can see that for silica fume and fly ash mixes. So the basic idea is that if you go down from 3 to 1 this way, or you reduce the porosity, your transport values really doesn't change that much. But if you go this way, where you reduce the pore connectivity, you can see from 8 per your non-steady state migration values going from 8.6 to 1.6. So pore connectivity is more important in transport, and pore connectivity is more influenced by the pore sizes than the porosity. And these are all from model based. So 2 or 3 different seemingly complicated things, but fairly simple at the end of the day if you think about connectivity being determinant, and connectivity being determined more importantly by the sizes than the porosity themselves within the range of porosities. We're not talking about 60% porosity. Story will be different then. But what you see in normal concretes, the size determines the connectivity than the total volume of pores. So one more reason for the pore size reduction in powdered sodium silicate concretes, and we did a lot of work on that. This is Fourier transform infrared spectra of both the powder and liquid concretes. You can see all the liquid concretes will give you that SI stretching vibration band at about 970 centimeters to -1, characteristic of a lowly polymerized gel, typical of what you see for CSH in cement systems. Whereas if you go to the powder activated mixes, that shifts to a higher wave number, about 10, 23, indicating a more polymerized gel. Your CSH is not getting more polymerized. What you have is, because of the inadequate dissolution, you're forming a sodium silicate gel that intermingles with your CSH gel, which is more polymerized. That's giving you this. And the sodium silicate gel, which you can see under microscope, is a very homogeneous, non-porous gel, which makes your overall porosity much lower. And therefore, the pore size is also lower. And therefore, the powdered sodium silicate activated mixes have reduced pore sizes. So they have lower strength. Strength is much more dependent on porosity, so they have all lower strengths, but they can give you better transport properties because of their lower pore sizes. So one thing to look for, even if it's not completely dissociated, one advantage of using a powder activated sodium silicate. Chloride concentration changes over the depth using particle-induced X-ray emission spectra. You can see how for powder and for liquid, now this plateaus very quickly. This takes more time to plateau off. You can fit in a fixed second law into it to calculate diffusion coefficient and a lot of other things from. And this is a very easy test because you take the entire specimen that was subjected to the test, just do proton emission at different depths and get the concentration profile. So here is some models to actually bring home the point of what is happening. And this is a very simplified version of the model. So here is your electrical impedance spectra that gives you the real impedance versus imaginary impedance. So this was done from 1 Hertz to 10 megahertz frequency range. And here is how we are doing the model for the concrete. So basically you have the electrolyte here. Chloride ions go from catholyte to the cell and goes inside. During the non-steady state migration duration, you are not going to get chlorides here because breakthrough point has not yet achieved. So your chlorides are only in the specimen, not going completely. So basically what you can say is my specimen now is just a combination of resistors and capacitors. The pore solution, the pores are the resistors, the solid phases and the interfaces are the capacitors. So if I use that kind of an analogy, and then if I look at bulk resistances alone before and after RCPT or the non-steady state migration test, you can see that generally after the RCPT test the bulk resistances come down, whereas after the non-steady state migration for a longer period of time your bulk resistances slightly go up. And I'll talk to you more about why that happens. So if you look at changes in the resistances, now overall resistance really doesn't change because only very small amounts of chlorides go in. So if you look at the effective resistance before and after, almost no change. But if I break it down into the connected pores and the unconnected pores, you can see the resistance of the connected pores goes up, which means connected pores are becoming more disconnected because you have some products being formed. The unconnected pores are you have to have that balance because this value is roughly the same. The unconnected pore resistance goes down. So the idea is number and connectivity of connected pores decrease. The same idea that I told earlier, that you have changes in connectivity, consequently pore sizes. and the reduction in connected pore resistance because some of the connected pores are converted to unconnected pores because solid products started to deposit. So we use this simple model to show what happens in resistance. And with that, we can explain what is happening here. So before and after, with non-steady state migration before and after. So connected and unconnected pores are more conductive after chloride transport, but more resistive. You have much more longer term for migration test that is slowly starting to change the characteristic of the pore structure, especially in the systems, as I told earlier, because the pore sizes are much smaller. Now, capacitance also are interesting because if you start to track capacitance and how capacitance has changed with time, you can look at understanding the solid product formation at the interfaces. So you can see this is capacitance. This is the interfacial capacitance. You can see that about 50% change in interfacial capacitance. This is for conventional concretes after you do a non-steady state migration test. So if you look at that, you can see that alkali activated slag and OPC concretes follow a very similar trend with non-steady state migration. So the takeaway from here is if you're doing an RCP test with alkali activated mixes, be a little careful because they don't really tell you, because it is dependent on the pore solution conductivity, the microstructure, the electrical properties, all of that. We like to use RCPT because it's pretty quick, you get a lot of good results, but for alkali activated concretes, RCPT will make them look better than what they are. Exactly like, if I may say, silica fume concretes. But non-steady state migration, which is 24 hours, but it gives you a much better indication of what's happening in the pore structure, at least from a point of view of comparison with OPC and alkali activated slag. You can see much similar behavioral trends when you look at the microstructure and how that changes with time. A quick way to predict the chloride content, and this is applicable to all types of concretes based on transference numbers. We are basically using the total charge passed as an integration of the current over time, and then you're essentially saying that, okay, I have non-steady state migration, which means I don't have chlorides on my analyte cell, which means all the chlorides are either in the catholite or in the specimen, and I can say that whatever is in the specimen is much lower compared to whatever is in the catholite because I have a very high concentration of chlorides in the catholite. So you can actually look at equating the transference numbers. You can do some simple operational procedures to do that and get the chloride concentration as transference number of chlorides times Q over F. F is the Faraday number, and a list of stuff that you look at it. And the comparisons between chloride concentrations from transference numbers and a few mixes that we did using Pixie. Very nice correlation and very consistent results too. And if you want to predict non-steady state migration coefficient, you can play around with Fick's law a little. Crank's book on diffusion gives the solutions for all of these. There are, lot of software. For example, MATLAB has now a new inbuilt Fick's solver. Fairly nice. So you can actually look at the total mass of chlorides that went through, and then you can use find the non-steady state migration coefficient. Basically what you do is, all you do measure the charge, and if you can really in the lab get a correlation, I can do only half an hour RCPT or whatever half an hour charge measurement, compare it, have a calibration chart, get that, extend it without doing a test, you can actually predict the migration coefficient. It makes a very easy, quick test, and then you can use this back to predict, based on what migration coefficient you want, you predict what is the activator content and activator concentration you want to get a certain transport property, a certain strength. So it gets you a big picture of combining both mechanical properties, durability with mixture proportioning. We still have to draw some more lines in between the triangles, but the three corner points are there, which we can use as a base. So just to summarize, I'm not going to go through all of that. Powder mixes consistently showed better transport performance, comparable or better performance for all these mixes compared to OPC concretes. Overall pore volume effects, which we talked about. One more. Reduction in pore size are more influential in reducing pore connectivity, and quantification using the results that I showed. Faster predictions. Thank you very much. I think I'm on time. If you have any questions. Yes, Mr.
Well explained why the reduction in transport property, increase in better resistance in transport property as a result of reduction in pore size. What is the explanation for reduction in compressive strength?
Well, compressive strength is much more connected to porosity. So if you have a higher porosity, because you lack material overall when you have lower porosity, so that is more related to compressive strength, whereas connectivity of pores is much more connected to transport.
But I was also thinking that compressive strength, in a way like all fracture property, may be related to
larger pores too. Yes,
maximum, and then
yes.
non-connectivity will increase.
Exactly.
So that might be what I was.
Right. So
when I compare that.
Exactly. So yeah, from a point of view of fracture properties, yes, the ligament length issue will come to picture. Yes. Yeah. That will be a good way to explain the reduction compressive strength. Thank you very much.